Thank you, Jean-Paul. Thank you, Tim, for this, for setting up the discussion so beautifully. I'm afraid I don't have pieces of cheese to guide my argument, but we actually arrive very much at the same space, I think, of the solution space. But let me first start with thanking a few people. First of all, Jan, for inviting me to be here. But more generally, I would like to thank IPGP. I spent 15 or so, beautiful years here from late 90s to about 10 years ago, working with many people, making many friends here. Many of you are in the audience, and I'm really very grateful for that experience. And I'm also delighted to see Kevin here. I think the last time we met was in Singapore, but even for the wrong reasons, I'm glad to see you here. And I'm also enjoying really today. I've not really participated myself much in the research over the past 10 years. And so what I've been hearing today is really kind of catching me up on, the fantastic progress that has been made in the last decade. It's also clear that, there's still very many open questions about, in particular, Tibet and the whole deformation of continental structure. But when I first started, I worked mostly safely sequestered on the 4th floor of the old building in the seismology group, working with Jean-Paul and Elinor Stutzman and other people. Satish was there. But sometimes I ventured out to the 2nd floor, very dangerously. Where of course I had conversations with the likes of Paul and Vincent Coutillo and Jean Bess and people there. And that started kind of a long tradition and a long collaboration I had with that group in particular also. Let's see, how do I move these around? Oh, just in the, it's easier. And then at the time I was at MIT as a young professor, and I started working on Tibet because several of my colleagues worked on Tibet. They worked on the surface and they wanted to know something about the deep structure. And I'm a seismologist doing tomography. And so they pulled me in. And then, of course, the conversations with Paul took a very different turn. We've heard about, the discussions about, cheddar cheese and brie and, the competing models. And I got a full share of that in the beginning. But it was actually great fun. So very quickly, I was introducing this discussion, the debate between these canonical models. We've heard a lot about the extrusion model, and Gilles is here. There was really phenomenal work that guided a lot of the conversations about Tibet, of course. And I learned a lot about this when I was here at IPGP, but then, of course, I went back to MIT. And I got the earful and say, don't listen to these guys because they only are concerned about faults. And by the way, the anecdote that was shared this morning about John Dewey and Paul Tapponnier, that rang true for me too, because this was my own experience here as well. The competing model at the time was kind of the distributed flow, or the continuous deformation and crystal flow. That was more kind of pushed forward by my colleagues at MIT. And of course, when I then came back to IPGP, then again, I got the earful, in less polite terms, I should say. We all know Paul, and when he has a disagreement, he shows it beautifully. And I know very few people that explain the disagreement with so much grace and beauty and power. But very quickly, I thought, okay, I don't like these dogmatic views. That's not my style. I do love science. So I was very intrigued by this whole discussion, and I just wanted to, get to the observations and to the data. So that's what we did, and we decided to work together and continue the conversations and try to get, to some kind of, maybe agreement was too much of an optimistic view, but at least try to understand where the real world is. And so we worked together with quite a few people. You recognize some of them. But then collaboration with Paul and his group really kind of, got substance here by working with Anne. Anne's here, and she gave a beautiful presentation this morning. So I don't have to explain all that much about that. But also I give credit to my student at the time, Kelly Kaukason. He's an Icelandic guy. He since went back to Iceland to work in financial sector. In 2008, if you know what 2008 did to the world in finance, I think he had some regrets. But he did a lot of work on the tomography that was part of the work with Anne and Paul. And I really have really good memories of working together. Remembering sitting in Paul's office, I was surprised sitting with Paul, when he really kind of did a text and he was really kind of fretting over every word that hit the paper. It was beautiful. So with Anne and Paul, we really took kind of a large scale view. And some of what is shown here is actually quite similar in concept to what was shown earlier by Jolivet. And that was basically a combination of the plate reconstructions that Anne and Paul had done. Plate reconstructions in the sense of finding out where the plate boundaries were at a particular time in the geological history, and then combining it with the information that we had from our global tomography to see where the material ended up at large depth. And then we were really kind of surprised and amazed rather by the very good similarity and the correlation between the position of the trench at a certain time and the structure of the slab at a certain depth. So once you have time and depth, you have this kind of the four-dimensional movie that you can play. You can do a few things, and that was the main conclusion of that paper, that first of all, we realized that even though subductive plates, of course, have an angle, but most of the material actually sinks just vertically. There's not a lot of lateral advection there. But once you have time and depth, you can also talk about sinking rates. And if you have sinking rates, you can make estimates of mental viscosity and the stiffness of the material. And it was really, I think, a very successful hybrid of these completely different types of data. Then back to MIT, I followed on that same idea. And we had this picture is very similar, and it's also very similar to what Laurent Jolivet showed earlier today. The main difference, I think, with what we did and what we did in the earlier study with Anne and Paul is that we realized, of course, that there's a very kind of the interplay of two dynamic systems. And it's not so, in our view, that you have the collision forcing the extension, and the extrusion basically works to a kind of a free open boundary to the east. But there you have a subduction system that is not just pushed away by the extrusion, but also helps actually to create space for that extruded material. And that is basically what you see here. So it's basically these two systems that work together, that you have the collision and the subduction of the Indian plate, causing the extrusion, but at the same time, that extrusion, the removal of that material from the center, was aided by the rollback of the slabs. Now, what we've heard today is, I find myself mentally kind of 20 years back, but there's still this discussion about, what is the main role of the extrusion and slab rollback and the full dynamics of it. It seems that we're still not entirely sure where that balance is. For myself, I'm pretty convinced that you need both of these systems to make it work dynamically. And this is not only happening in Southeast Asia. I mean, there's a similar mirror image happening in Arabia, with Arabia, the microplate moving north, and basically you have then the trench system, the rollback in the west, and that also kind of gives rise to the North Anatolian fault and the extrusion of the movement of Turkey to the west. So then you can, of course, combine it with a bit of geology, and that this is very similar to, to what people have done before. But, so you have this material being kind of squeezed out of the central collision zone, aided by the rollback of the slabs. And what is then critically important, that was at that time to us, and also to distinguish between that model of what Tim calls the brie and the cheddar. We looked at a particular area where, we could perhaps test some of these ideas. And that's by looking at Southeast Tibet or Southwest China in Sichuan province and Yunnan province. And so that's where I basically came in and, worked a lot in seismic imaging of that particular area. And that was great fun. I mean, I was actually trained as a geologist, but so being in the field is one of my passions, and doing field experiments with seismology is always, just fantastic. So we put in about 25 or so instruments, seismographs, I should say, in the southwestern part of China, just around Sichuan Basin and a little bit further west in the foothills of the plateau. We worked together with a group at Lehigh University, and of course you meet fantastic people here. And they helped us, dig the holes. And if you look at the original picture, you see the man to the left smoking pipes and not doing anything. But that was part of the cultural experience. So we did this in 2004 when we deployed, say, as I said, 25 seismometers that we thought was pretty ambitious already at the time. But then some 10 years later in China, they were kind of the beginning of the Sinoprobe projects. And they had very, very dense arrays of seismographs. And that gave rise to, completely new types of discovery and new types of possibilities in seismology. So you can see the location of a few hundred of these seismograph stations here. And then you can really follow the wave field, how the waves propagate through that medium in extraordinary detail. Here you see a bunch of seismograms measured along that line here shown on the map. You see on the dark parts are the high frequency waves, the P waves and the S waves. The more extended wave train is the surface waves. And you can do all sorts of beautiful seismology with that, but then at much higher precision and resolution than what we have been able to do before. The particular technique that we deployed with our colleagues in China at the Institute of Geology was a combination of classical tomography, surface wave tomography, for those of you who are familiar with those techniques, or with receiver functions. And receiver functions are basically you have the effect of a wave impinging on a boundary, for example, the MOHO, and then you look at the difference between the P wave and the S wave, and that can really help you constrain the wave speed in that layer above it. And by combining those techniques, we were able to create very high resolution models. And one of the questions that we asked, again, going back to this debate about, continuous flow or crustal or channel flow versus, these extrusion models, was to look for, evidence for these weak layers. If you have crustal flow, that means that the material is weak. In seismological terms, it probably means that the seismic wave speeds are low. Particularly the shear wave speed, that's basically a function of the shear modulus. So if you have low velocities, then you have probably a low modulus and low mechanical strength, which might enable flow. It doesn't mean that you have flow, but it actually is conducive to flow. So we were very focused on finding areas or evidence for these low velocity channels, and we actually do find them. They're quite ubiquitous in Tibet. I can also tell you that they're not continuous. I think that was said before today. And that has ramifications for the horizontal extent of any flow that you might have. But you see some really dramatic differences between, for example, this cross-section here, down to about 100 kilometer. You have the MOHO there, so we have a very thick crust, as we know in Tibet. The top is the topography. So we have the Tibetan Plateau on the left in the cross-section, and then the flat area, the Sichuan Basin, on the right. And it's a very strong, mechanically strong part. The cross-section is shown here. And that goes across the Long Wenshan Fault, the Wenshan earthquake, a few years before this study. And what you see there is a few things. First of all, you see the MOHO kind of irregular. It's a bit ambiguous where you would pick the MOHO, but you see then a fairly sharp jump right at the side of the Long Wenshan Fault to a fairly flat MOHO, the crust-mantle boundary below the Sichuan Basin. What you also see is that in the wave speeds themselves, you see these stretches of low or red, which is the low velocity. So we see these areas of low wave speed, i.e. mechanically weak zones, throughout the crust, but mostly in the middle crust and in some parts the lower crust. And what you see here is that all these things, they change. The topography changes, the moho depth changes, and the low velocities, they stop quite abruptly at the Longmen-Chant fault. That is very different than if you look at this side here, where you go from the Shanxue fault to the southeast across the Lijiang fault, where you see a much more gentle slope of the topography. So you don't see that very abrupt change what you see if you go from the plateau into the Sichuan Basin further to the north along the Longmen-Chant fault. You see a very gradual decrease in the topography. The moho is still showing a jump, but if you now look at the low velocity layer, it's very pronounced. Just south of the Shanxue fault, it's a very pronounced low velocity layer, so probably mechanically very weak. But it actually continues across the fault and across the what we usually would call the boundary of the western boundary of the South China Craton. So the manifestation of these low velocity layers in different parts of Tibet or eastern Tibet is quite different. And so we matched that with compare that to the predictions or the models of my colleague Lee Royden at MIT. And so then the boundary across the Longmen-Chant fault actually looks more similar to what I would call the laterally constrained part, where you have this very strong crust on the east side in the Sichuan Basin, and you do have low velocity layers and mechanically weak zones to the west of it, but it really stops abruptly at the place where you have also the strong topographic change. As opposed to what I would call the laterally unconstrained one, where you do allow flow across the boundary. And that is more kind of the depiction of the lower right. So as I mentioned, we've been able, using that very dense array, to map that out in quite detail. This is not very exciting to look at unless you're a seismologist working in the area. But the most important thing that I want to point out is that we do see this evidence for these red areas, for the mechanically weak zones, but they're not continuous. They are laterally very variable. And if you do have mechanically weak zones in the crust, they are probably very limited by these very big faults. These are some eye candy for three-dimensional renderings of the same materials. But what you see, for example, in our summary of it in the lower right, again, you see this orange reddish color. It's really to the southeast of the Shanxue fault. And in the Zhongpan, it's very different. And so the contrast between the plateau and Sichuan bases to the north of Shanxue fault and the south has a very different manifestation in the seismology. Then if you combine that, of course, with data, the type of data that Tim showed earlier, and that has been shown earlier as well in terms of the displacement rates, but you can look at the strain rates, you can do whatever you want to do. But there again, you see that the area to the southwest of the Shanxue fault is very different in its behavior than further north. And there's a lot of detail to be seen. We also looked at the seismic anisotropy, and also the seismic anisotropy shows that the upper crust and the lower crust and the upper mantle, they actually behave in quite a different way. So there's clearly some mechanical decoupling going on in some of these areas. So there is seismological evidence for weak crustal layers that might enable flow. I'm not saying that there is flow, but it's quite likely that there is flow. But there's also a lot of lateral variability. And so if you do have flow, this variability that may really limit it. What I didn't emphasize here, but is also very obvious from our tomography, is that often these very low velocity zones in the map view, they are kind of intersected by areas of much higher velocity, which in our parlance then means, strong area. So you can have local deformation that is very strong in the middle and lower crust, but it's certainly not continuous across very large areas. So that was the conclusion of the work that we did with our colleagues in China, is that, yes, in the southeast part of Tibet, you can see that the eastward expansion of the plateau probably happens both by crustal flow, but also the partitioning across faults, very similar to what Tim showed earlier. So it's kind of a combination. Nature doesn't like dogma, and it just does what it wants to do. And as is very often the case in nature, if you look very carefully, then the old kind of ideas that it could be very antagonistic, often, the truth is somewhere in the middle. Given the discussions of today, we don't know where exactly in the middle it is, a little bit off to the left or to the right. But that's not so important, and that's why further research is, of course, important. The acknowledgement of this paper, of course, we acknowledge Paul. I had many conversations with Paul. He became a very good friend over the years. Mo Deves, we had many discussions with in terms of, to what extent shear itself could kind of, affect the temperature, could have shear heating, whether that could give a runaway effect, and all sorts of interesting ideas that we didn't really follow up. But I would like to thank Paul here. He's not with us, but he's probably listening somewhere. For the many fantastic years that I have with him, I've learned a lot. And I want to stop there and thank you, everybody.